Good morning. I'm continuing with my discussion of quantum mechanics. It's going to be lesson number or lecture number 4. So you say, where's 1, 2 and 3? 1 and 2 I did a long time ago. They are on the fine structure constant. You need to have a look at those two. All right. 3 I haven't posted yet. Windows 10 plays games with its users as well as, attacking the user's privacy. It prevents me from loading anything over a certain number of bits onto the computer. Okay, so once this lecture goes over a half an hour, Windows 10 won't let me put it on the computer. It's one of the things that it does. So I have to stay under a half an hour. I'm checking my clock to make sure that I don't go over, let's say, 28 minutes. So I'm continuing with lesson number 4, quantum mechanics, and I'm going to talk about the essentials, wave packets, Fourier transform and how it's related to the Heisenberg uncertainty principle. Now I want to focus in on the essential physical principles in quantum mechanics, and this lecture and the next will do that. After that, quantum mechanics becomes a blurred issue to the student because you get involved with the formalism. The formalism of, let's say, eigenvalues for differential operators, eigenvalues of a matrix, state vectors, Hilbert spaces, all these things. So that clouds the issue for quantum mechanics. The path integral even clouds the issue a little bit. So basically quantum mechanics is kind of very simple when you just look at the physics, and we'll start by doing that today. Now the two numbers that get involved here are Planck's constant and the reduced Planck's constant. Crucial numbers. I also have a presentation on Stoney units and how to get from Stoney to Planck units. Whether h is the fundamental constant or the charge on the electron, that's not entirely clear. But it's all related to the fine structure constant one way or another. And that's why I suggest you look at this stuff. I try to look at the essence of quantum mechanics. I have a slightly different way of looking at the big picture of quantum mechanics, by the way. To me, what gets quantized are the levels of the energy, energy levels in the electron. That results in the photon quantum. Now in lecture number 3, you will see that Planck says that the energy of a photon is given by h times its frequency. H times its frequency is the first crucial equation for quantum mechanics. Alright? Now let's rewrite that. Now from circular motion, I have a circular motion class on the web as well. You'll have a look at that one. In classical mechanics, 2 pi times the frequency is the angular frequency, and this part here is h cross, so that's going to be omega. Anytime we see an omega in an equation, such as the following, we could replace that with an energy. Let's look at the second crucial equation in quantum mechanics, and these two are really the building blocks along with Heisenberg's uncertainty principle. This addresses the electron, this addresses the photon, and this one addresses the electron. The momentum is what's crucial when we come to the electron, and it has momentum h over lambda, and we'll do the same thing. K is the wave number, it's 2 pi over lambda. I'm going to be working in 1 dimension, but we could move to 3 dimensions very easily. 3 Cartesians, 3 polars, whatever set of coordinates you choose, that's always possible. Now h over 2 pi is h cross again. 2 pi over lambda is the wave number. So therefore then, anytime I see a k in an equation, I can write it as p over h cross. Anytime I see an omega in an equation, I can write it as e over h cross. So this can be rewritten like this. This is really quantum mechanics, and this is more obviously quantum mechanics. This will generate an equation in P and E, which we will call the Schrodinger equation. So this is these are our crucial steps for quantum mechanics. This actually contains 99% of everything. So now we'll look at wave packets. Now, lecture number 3, when it gets put up, deals with the 50 years between 1850 and about 1900, when people like Wien, Radiant Jeans, Max Planck, who else? Lots of people were involved in the study of what I call the radiation problem. Radiation being, what happens when light is emitted from a cavity radiator? Why does the color change? What's the energy relationship? So on and so forth. That's a big issue. I'm trying to make a short version of the big long talk that I gave so that I can post it in a 20-minute or less lecture. This is our building blocks so far. Look at this and this. Here's another object we'll talk about. Let's take a point, xy, as measured in this frame, and x dash y dash as measured in a frame that differs by an amount a. Well, x dash, the coordinate of this point, is going to be this whole distance less the a. Well, the a could be changing. It could be vt. This could be moving at constant speed. Well, it could be the speed of light. So, what happens? We're essentially translating the coordinate system. Not only that, but f of x translated looks like that. We can translate any coordinate system and any function of the x variable, x minus ct, ends up looking like that. Well, basically that's what's happening up here. Actually, let's do that. Let's see why that is the case. Let's take this oscillating function and translate it so that not only is it oscillating like this, it's moving along, so therefore what happens to it? It becomes, first of all, it starts off like this, but now it's moving as well. Each one of these humps has a speed c. So it's a wave. That's what this thing is. So this is a wave moving in the positive x direction. So, lambda cancels because c equals frequency times wavelength. and I get the result that I put down there. 2 pi f is omega. Okay, so far so good. So now that I can clean everything off the board, and we're moving ahead now to look at the wave mechanics. Now, a common idea in Fourier analysis that if I have a function e to the power of minus alpha x squared, which is a Gaussian, its Fourier transform will have a form that is reciprocal to it. Okay, I'll just put this thing in fx, let's say g of k or something. Alright, so the x dk, whatever that is, is going to be of the order of 1. This reciprocal behavior is something that crops up in Fourier analysis. It's actually what leads to the Heisenberg uncertainty principle before we actually state it in terms of operators. So, we will take a wave packet. We won't translate it yet, we'll have it centered around, let's say, K0. Let's see. I'm going to take a situation whereby A is 1. We're going to say that g of k have this form. It's a Gaussian, so it's going to be centered around K0. Now we're going to look at the half width at half maximum. You have to look up at that. When we go halfway up, the value of the function, there it is there, and this bit there. The half width at half maximum is this much there. Actually, it's when the function falls off to 1 over e of its original value. Okay. So, let's work out this. I'm multiplying and dividing. I'm multiplying by this guy and then multiplying by this guy or dividing by that. Now, so this quantity is 1. So I'm going to take that outside. This is the alpha. This is the function I'm using for g of k. So that's our f of x is the Fourier transform of that. Uh-oh. form of the function, I have to integrate that thing out. Let's see. So that's what I've got to integrate out. So I'm going to integrate this by completing the square, because here's the result. It's famously joked that that's the only integral that physicists know how to do. But it's not entirely true. Physicists can do a lot of integrals. So I'm going to write it like that. So I'm going to complete the square, have the coefficient of x to be squared has to be subtracted. But don't forget there's a negative thing here. Okay, and this bracket, I'll make it a square one, because that's an error. If I ended up with a positive sign on this thing, I wouldn't get the right answer. So therefore then, I can work out this integral now. I'm putting this back up here. So this whole thing goes up here. Now dq and dk are all the same thing. And that should be squared. So that's the integral I have to work out. You don't need these ones here. Q plus I alpha this is a Q. And the differentials dq, d big Q, and dk are all the same thing. Now the big Q drops out and doesn't show up in the integral. This one here. So I get our result, okay? And that's going to be the f of x. So I'm going to put it up here. This is our result. That becomes alpha gives away 1 power of that, q squared over 4 alpha. So, now remember what g of k was. E to the minus alpha q squared, where q is k minus k0. So the half width at half maximum so if I go this times its complex conjugate, I get that. Okay? Now, for gk, same thing. So we're going to see that the half width of half maximum is proportional to 2 alpha and proportional to 1 over 2 alpha here. So we get, now, we have to multiply by a factor of 2, but it doesn't matter. Really what we're getting is this. For a Gaussian, we can say the following. That's a result. And for its reciprocal, it's going to be a constant times root alpha times a constant times 1 over root alpha. So it's a product of two constants. Actually, there's going to be a factor of 4 in there. All right? So therefore, then we're writing up onto the Heisenberg uncertainty principle, because here's what happens. Remember what I said k can be replaced by? Now this constant we just call C3. Heisenberg uncertainty principle, it's showing up already, although we have yet to determine what that C3 is. Okay? Now I may have run out of time here. There's more coming up next. The next part we'll deal with will actually derive the Schrodinger equation. And that really is 99.9% of quantum mechanics. The rest are applications. Okay, so this is a wave packet. Now if I go like this, I essentially cause the wave packet to propagate in the x direction. And omega itself might be some function of k, and we could have to expand that out in a Taylor series in order to study it. That'll do for now.